When performing a titration, the solution in the burette is known as the titrant. It is a solution of known concentration, which we call either a standard or a standardized solution. A specific volume of the analyte is pipetted using a volumetric pipette into an Erlenmeyer flask. The titrant is then carefully added to the analyte until the first permanent color change appears in the indicator. So we're going to add an indicator to our analyte, which is in the Erlenmeyer flask below. So this is our analyte containing an indicator, and inside the burette is our titrant. And we're going to open the valve here to slowly add our titrant into our analyte until that first permanent color change occurs. And that color change is known as the transition point or the end point. It should signal when the equivalence point in the titration has been met. So remember, the equivalence point is when the amount of hydroxide ions equals the amount of hydronium ions. So it's important to note that the transition point and the equivalence point are independent of each other. The transition point is dependent on the chemical nature of the indicator, whereas the equivalence point is dependent on the chemical nature of the reacting species. So the transition point is depending on which indicator I use. Each indicator changes color at different pH ranges. And the equivalence point is going to depend on which acid and base I am reacting together. It's up to the chemist to use an appropriate indicator where the transition point is close to the equivalence point as possible. Obviously, if the indicator is helping us mark the endpoint, we want that endpoint to occur when the equivalence point is happening, right? If those two things are not happening at the same time, then our results are obviously going to be impacted. So once the transition point or endpoint has been reached, we're going to close the valve on the burette, and we're going to measure the volume of the titrant that we added to the solution. To account for errors such as incomplete mixing in our flasks, or incorrect pipetting techniques, or errors in reading the burette, we're going to perform multiple trials. And we want to make sure that those trials are within 0.1 mils of each other. And so when we are looking at determining the average volume of the standard solution that we added, so the average volume of our titrant added, we should make sure that we are eliminating any outliers. So for example, in this data table, we would actually exclude the first trial because it is more than 0.1 mils out from the other two trials. So the average volume of standard solution that I had add would actually just be an average of the second and third trial, which works out to 21.20 mils.